All right, so I apologize again that it's not going to be swiveling today, but at least this means I can get outside the range of view without having it following me. So what I want to do today is I want to talk about basic feasible solutions and basic optimal solutions. So basic feasible plus basic optimal. And then if there's time at the end today, I want to talk a little bit about some of the homework problems, especially the one on the Euclidean algorithm. So this is the first lecture where we're going to really use the stuff from linear algebra that we were supposed to have learned. All right. So far, we've done a little bit on linear programming. We looked at the dyad problem, and what was the very nice thing about the solutions for the dyad problem? I'm sorry? You only have to check the vertices. Now the problem, of course, is the number of vertices can still be astronomically large and too large to be practically useful. Yes?
What happens if, so we can't, say the vertices need a half and a half, and we're talking about units,
Right.
where we can't get to the vertices.
That's a different problem. That's integer programming. And so if you require yourself to have integer solutions, that's a very different problem than what we're doing right now. And right now, we do not have any way to solve something like that. And unfortunately, one of the great difficulties is that the optimal integer solution may not be anywhere near the optimal real solution. So there's a very famous problem called the knapsack problem, which we'll study later, which just shows you how bad things can be. And when we're trying to look at this, I will actually give you my favorite problem from calculus. It essentially uses almost everything you learn in Calc 1 in one problem. So it's a great way to review Calc 1. Now, unfortunately, that's not really the class you need to review. It'd be much better to have one problem that does all of linear algebra. I sadly don't quite have that yet. But we will see problems where the integer solutions sometimes are and sometimes are not near the real solutions. OK, so going here, we at least hope that we only have finitely many things to check. Finitely many is at least doable. Infinitely many, we're not going to do that on our computers. We then want to find a good way to navigate that forest of finitely many things to check. This is going to be the simplex method. And the way it's going to work is the following. Here's the idea. If a feasible solution exists, then a basic feasible solution exists. And here we say x is basic feasible if the following is true. X is greater than or equal to 0. And then if ax equals b and the non-zero entries are xj1, xjk, then the columns aj1 through ajk are linearly independent. And so I'll remind you what linearly independent means in a moment. Right now, there's just a very simple condition to tell if you have a basic feasible solution. Well, the first part is if I have a feasible solution, I'm supposed to have x is non-negative. I'm supposed to have ax equals b. This is one of the advantages of having a canonical form of our linear programming problem. Is I can say my solution has to be of this general form. It's got to be of the form x is non-negative, ax equals b. So if I'm going to go from a feasible solution to a basic feasible solution, it seems reasonable that I have to add an additional constraint on my set of solutions. I want a solution that not only is feasible, but has some additional property. So the question is, what would be a good additional property to have? And the good additional property to have is that the columns are linearly independent. So even though the camera can't detect it, I'll just write it over here. So basic feasible, x is greater than or equal to 0, ax equals b, if xj1, xjk are the non-zero entries, then the columns aj1 A, J, K are linearly independent. Right? So that's my condition to be basic feasible. This is a really nice theorem if this is true. If a feasible solution exists, then a basic feasible solution exists. I didn't bother to write this as an if and only if. Do you think the other direction holds? If there's a basic feasible solution, is there a feasible solution? Yes. One direction is really not that interesting. But what this tells us is that if you can find a feasible solution, well, okay, I should be very careful. I'm not a theoretical mathematician today, I'm an applied mathematician. I was going to say, if you can find a feasible solution, you can find a basic feasible solution. I'm going to be very careful about using words find. If a feasible solution exists, we will show a basic feasible solution exists. Instead of a feasible solution, what's another word you would love to have? We don't want a feasible solution. What kind of solution do we want? Optimal. So this is also going to be true. I can replace the word feasible with optimal. Okay? That's going to be a great lemma. It's going to tell us that we can restrict our searching to just the basic feasible solutions. If there's an optimal solution, we can find an optimal solution among the basic feasible solutions. This is going to really narrow down the search space. Okay? What if there is no optimal solution? Will there be a basic optimal solution? No, right? If there's no optimal solution, it's ridiculous to try to say, well, okay, I want an optimal solution that has this additional property when you don't even have an optimal solution. Similarly, if you don't have a feasible solution, do you expect there to be a basic feasible? No. Right? So these lemmas are exactly what you would expect. What I want to do quickly before I do the details is I want to just review what it means to be linearly independent. So we say V1 through Vk are linearly independent if alpha 1 V1 plus alpha k Vk equals 0, if and only if alpha 1 equals alpha 2 equals alpha k equals 0. And I've deliberately made one mistake. What mistake have I made? Really small mistake, but. I'm sorry? Okay, 2. So I will assume all the VI are non-zero. Yes. If any of the VI are 0, it's trivial. Just take the thing in front of it. Yes?
That's the only time that the alpha I VI that sum can be equal to 0.
I'm sorry?
That's the only time. It's only if the alpha are all equal to 0 that the alpha I VI is that sum.
Yeah, I mean, it's not wrong to say if and only if. One direction is, again, trivial. If all the alphas happen to be 0, this is going to equal 0. Oh, okay, but yeah, we'll do it as a then. If this is a really small mistake. It's a typographical mistake.
Oh,
Yes?
0 vector.
This should be the 0 vector. All right. It's really worth spending time whenever you have quantities to ask yourself, what kind of quantity is this? Is it a number? Is it a vector? Is it a matrix? Is it a function? Where do these things live? This is a vector. It should have lots of components. So I'm saying the only way I can sum these vectors and get to the 0 is if I take 0 of each one. This is crucially related to things such as dimension when you do linear algebra. So again, what city do I hate? New York, right? But I have to give New York credit for what? The street systems in Manhattan. So Manhattan is very nice in a grid like this. If I take a vector pointing in the east direction and a vector pointing in the north direction, can I have a multiple of the east direction plus a multiple of the north direction equaling 0? Only if both are 0, right? If I go 0 steps east and 0 steps north, I've gone 0 steps. Great. There's no way for me to move a non-trivial amount east and a non-trivial amount north and end up at the origin. Okay? What if I add a third direction? So I now have 3 directions like this. Can I get a linear combination of these 3 directions to be 0? Yes, I could go 1 unit like this, maybe 2/3 of a unit like this going down, and then maybe negative of that, and I'll come back home. Or maybe better yet, 1 unit like this, 2/3 of this going up, and then negative 1 unit of that will bring me backwards. So these will be linearly dependent. And in fact, there's a basic theorem here that if you have more non-zero vectors than the dimension of your space, they will always be linearly dependent. You can always write one of them in terms of the other. Is it a theorem that if you have the same number or fewer vectors as your dimension, they will always be linearly independent? Is that a theorem? No. Give me a counterexample. Yes? Yeah. I was going to say, if just a bunch of people raised the hand at the same time, those would be the answers. Right? If the vectors are in the same direction, clearly that's going to be linearly dependent. Okay, so this is one of the key concepts in linear algebra. I know it's been a while since some of you have taken linear algebra, and I've also heard some things through the grapevine, so I just want to make sure we're all on the same page. I'm not saying I heard anything about linear algebra through the grapevine, I'm just saying I've heard things about various things. All right, so this is the concept of linear independence. The question is this a good concept? Is this a good restriction to make a class of solutions? We can define anything we want. When is it useful? Well, here, when we have a solution, we're looking at ax equals b. And so what I want to do is I want to talk a little bit about what does it mean to calculate ax. So if you have a matrix A and a vector x, I can write A as the columns A1, AN, and then my entry is x1 through xn. And I do the multiplication. Typically, you look at it as a11 times x1 plus a12 times x2, et cetera, like this. There's another way to view this. This is the same as x1 times the first column plus x2 times the second column plus xn times the last column. This is another way to view matrix multiplication, a matrix acting on a vector. And if you just think about what's going on in terms of what the different entries are going to be, when I sum everything up, I'm just splitting my things up. It's still going to sum to the same thing. So when you're looking at the output, when you're looking at A times x, you're looking at linear combinations of the columns. So if you want this to equal b, where must b live? We need b in the what? Yes, what's the phrase? Okay, in the span of A1 through AN, but there's a special name for this in terms of the matrix. Which is it, row space or column space? Columns, we're talking about linear combinations of the columns, right? In the column space. A lot of books talk about the fundamental theorem of linear algebra, where you have the 4 different column spaces. For the 4 different spaces, you have the column space, the row space, and then you have the similar things for the transpose. I've never really liked calling it the fundamental theorem of linear algebra. I think it's putting on too much of an air. To me, it's not nearly the same as fundamental theorem of calculus and all these other fundamental theorems, but had good marketing people, got the name in a lot of textbooks. All right. This is the column space. We're saying we have a linear combination, and the only way we can get a solution ax equals b is if b is in the column space. So if b is not in the column space, there is no chance of finding a solution. In general, what do you think the column space of this matrix is going to be? Do you think it's going to be all of Rm or a subset of Rm? So this lives inside Rm. Do you think, as I vary over all x's, do you think I'm going to get all of Rm or just a subset? Well, because all of our matrices, they always have n columns and m rows. So m rows, n columns. Which do you think we have more of, rows or columns? And again, either one is fine, but in applications, which do you think is going to be the case? Columns. If we had more rows than columns, the system would be overdetermined. Right? There's at most one solution. The subject's not that interesting. The subject is only interesting because typically n is greater than m in applications. And because n is greater than m, we actually have multiple solutions in general. And then we're trying to find, of all the solutions, which one is best. Okay? So for something like this, we expect this to be all of Rm. If I choose a matrix at random, is it possible that my column space is not all of Rm? Yes. It's unlikely, and often a small perturbation of the matrix will keep it so that it's all of Rm. So one of the assumptions we'll make when we get to the simplex method is that the column space is all of Rm, or at the very least that B is in our column space. All right, so we're looking at this. So this is another way of viewing Ax equals B. I'm trying to motivate why we look at basic feasible. When I look at this linear combination, which x's matter and which x's don't matter? I'm sorry? Well, what do you mean by linear independent? Because I'm looking at the x's. Which entries of x matter? Which entries of x do not matter?
So one's like, if you were to pare down that to linearly, like the ANs, the ones associated with that would matter.
Okay, so we definitely want to get there, but and how do I do that in terms of the x's?
First, every non-zero one doesn't matter.
No, no.
Everyone-
Take the opposite of that. Yeah, we'll try to edit that if that was ahead. So if an x is 0, does it matter what the corresponding column is? No. Does it have any role here when I look at Ax? The only columns in play are the columns where the entries of x are non-zero. And remember, x is never negative. Its components are always non-negative. If a component of x is 0, it doesn't show up over here. And so now that allows us to go from something like this to we can now erase this, and we'll just go through the non-zero ones. xj1, aj1 plus xjk, ajk. We'll assume we have something like that. Okay? And now we can assume all these xji's are strictly greater than 0. And these are the only ones left. So now we're very close to getting to the condition of basic feasible. We're looking at the linear combination. And now I say, let's call a solution basic feasible if when we look at this linear combination, the columns aj1 through ajk are linearly independent. Well, the idea is if they were not linearly independent, I should be able to replace some of the columns with some of the others. If there's a linear dependency, I can somehow make a few more of my x entries 0. And I'm going to somehow winnow things down to a minimal solution. Okay? This is where the notion of basic feasible comes from. If we had linear dependence among the entries, that would lead to the ability to create a new solution from that that would still be feasible. Okay? So this is the idea. If columns are linearly dependent, we can winnow. And that's what we're going to be doing in a moment. We will be winnowing. Okay? So this is going to be one of the major proof techniques. Is you prove that you have an object that has a certain minimal property. And then you show that you can get something with an even more minimal property. Well, that can't happen, so there's a contradiction. All right, so what I want to do now is we want to show that if we have a feasible solution, there is always going to be a basic feasible solution. Okay. Any questions so far on any of this? All right, so I do apologize, but today real estate is extremely precious as the swivel technology is not working. So I'm going to erase this. I will keep the notion of basic there. So the first question is, how many basic feasible solutions do we have? How many basic feasible solutions are there? What are the two possibilities? Very general. All right, 0, but 0 falls into a certain class. Finite. Or, what's the other one? Infinite. So we clearly want it to be finite. We want to have a small set of things to look at. Okay? So it's finite. And here's the proof. So if you have a basic feasible solution, the columns have to be linearly independent. What's the maximum number of columns you can have? M. So have at most M columns. And so how many ways can I choose at most M columns from N? So the number of choices is less than or equal to the sum, little m goes from 1 to big M of n, choose little m. Why do I start at 1 and not 0? Yes?
Yeah, and choose 0 columns for another choice.
Yeah, although maybe then my x would be all zeros. It would be the 0 vector. Should we allow that or not? Does it really hurt us if we start at 0? So this is called CYA. This is being recorded, so I will not elaborate on that. But why not just give ourselves a little extra protection and include the case of having no columns chosen? Maybe the solution is just have all the x's equal to 0. And then we have to decide, do we want to consider this a solution or not? My freshman year in college, I had a textbook, and it actually said the following. Whenever the empty set would cause problems in the statements of theorems, we tacitly exclude it as a possible vector space. So they never went through and said in the theorem, when you're not excluding it, they said, oh, come on, we assume you're going to be smart enough to figure it out. For something like this, we could have issues. What if the solution is just all zeros? So let's just allow ourselves to choose 0 columns. What can you tell me about this sum? It's finite. It's less than or equal to 2 to the n. You can do better than that. And I think that's going to be maybe one of your homework problems, is try to estimate how large is that sum going to be. But it's going to be at most 2 to the n. It's a finite number. So we have only finitely many sets of columns that could potentially be linearly independent. And then we just need to see how many solutions. So let's fix a set of columns. So fix aj1 through ajk linearly independent. We need to show only finitely many feasible solutions. All right. So I'm going to let A be the matrix aj1, well, let's call it A prime, dot, 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 ajk. So this is a truncated matrix. I've thrown away all the entries of the matrix A that aren't involved. And I want to solve A prime x prime equals B. And we want to show there's only finitely many solutions to this. If we can show there's only finitely many solutions to this, we're done. Why are we done? Well, there's only finitely many ways to choose columns such that they're all linearly independent. And if each choice only has finitely many solutions, finite times finite is finite. Excellent. So we just have to show there's finitely many solutions to this. How many solutions are there to a linear algebra equation? What are the possibilities? 0, 1, and infinity. Okay. So unfortunately, because infinity is a possibility, we have trouble. If you have 3x equals 5, how would you solve this? You would what? Divide by 3, or more mathematically, multiply by 3 inverse. So I'm sorry? So wouldn't it be wonderful if we could just take the inverse of the matrix? So we don't know if we can. The columns are linearly independent. Can I take the inverse of A prime? What might cause trouble in taking the inverse of A prime? Yes? A might not be a square matrix. So unfortunately, A prime inverse might not exist. If it did, we'd be done. If A prime existed, take A prime inverse of both sides, and now you get there's a unique solution for x. So the only difficulty is, well, what if there's no inverse? Consider A prime transpose A prime. This is a new matrix. It turns out this is a k by k matrix. All right, so I will write it over here. A prime transpose A prime is k by k. What do you think is true about this matrix? I'm sorry? What do you think is true about this matrix? It has an inverse. What do you think is crucial in proving that it has an inverse? I'm sorry? The what? The determinant? We haven't talked about determinants in here, so not quite determinant. It's not a bad thing to try, but it would not be so easy to get your hand on the determinant. What do you think we're going to have to use to prove that A prime transpose A prime is invertible?
We should also show that the columns are linearly independent of the product.
So we want to somehow show that the columns are linearly independent here. What do you think is going to be crucial in that calculation? Yes, somehow at some point in this problem, we better use the fact that A prime has linearly independent columns. If we're not using the fact that A prime has linearly independent columns, this is false. So can anybody give me an example of a matrix that has linearly dependent columns such that A prime transpose A prime is not invertible? Do not think too hard. Yes?
0.
The all zero matrix. Right? All zeros all the time, all the places. Right? This matrix is not invertible. Somehow we have to use the fact that we have linearly independent columns. So then this is going to be one of your homework problems. Prove that if A prime has linearly independent columns, A prime transpose A prime is invertible. So this is one of the homework problems for next week. And a hint is to look at the null space. It is, show the null space is just the zero vector. And if the null space is just the zero vector, it's invertible. So this is where we're going to start to need some of the results from linear algebra. All right, so this it turns out to be invertible. So I will just write down it is invertible. Well, now that it's invertible, we're done. Now we get x prime. I first multiply by A prime transpose on B, and then I multiply by A prime transpose A prime inverse. So I'll write that over here. So we get x is A prime transpose A prime inverse A prime transpose B. Let me see, did I drop a transpose? No, I didn't. And so now we have an x. And in fact, there's a unique x. Is this x basic feasible? How many people say x is basic feasible? Not one person says it's basic feasible. Why might it not be basic feasible? So what's the problem? Why might this not be basic feasible? Yes? Excellent. The entries of the vector x may not be greater than or equal to 0. Well, we're just trying to prove that the number of basic feasible solutions is finite. At most, how many basic feasible solutions does each set of linearly independent columns generate? You give me a set of linearly independent columns, it generates at most how many basic feasible solutions? At most, 1. It may not generate it. What you get may not be a feasible solution, but it generates at most 1 feasible solution. Well, if it generates at most 1 feasible solution, and we only have finitely many of them, then finite times finite is finite. And in fact, this is finite times 1. Okay? Is it worth trying to figure out how many times this is feasible? Not for this. For this, we just want to know that it's finite. Yes?
Are we calling it x or x prime?
You're right. We should probably call it x prime. And then, of course, if you give me an x prime, I can inflate it to an x by just padding it with zeros. All right, so this is our first result, that there are only finitely many basic feasible solutions. Okay? Any questions about this proof? Okay, now that we know that there's only finitely many basic feasible, what result should we prove next? That would be wonderful, but we need something before that. So we know there's at most finitely many basic feasible. So what do we want to prove next? So we want to show that it's enough to just study basic feasible. So we want to show is if a feasible solution exists, a basic feasible solution exists. That's the next thing to show. Question?
Does the number of feasible solutions have to be less than or equal to the world damage?
There can be infinitely many feasible solutions because by using linear dependencies, you can actually get infinitely many copies. That's one of the whole reasons, that's a good question. This is one of the reasons why we want to restrict to basic feasible. It makes our set for searching finite. So we want to show now that if there's a feasible, there's a basic feasible. What if there's not a feasible solution? Do we care? No. Why don't we care? Yeah, if there's no feasible solution, there's no basic feasible solution. If there's no feasible solution, there's also no optimal solution. So if you can't do it, you can't do it optimally. Yes?
Can you say one more time why we care about the basic feasible solution?
So there's only finitely many basic feasible solutions. And it's going to turn out that if there's a feasible solution, there's always a basic feasible solution. If there's an optimal solution, there's always a basic optimal solution. This is going to allow us to restrict our search space greatly. There's infinitely many potentially feasible solutions. This really narrows down our searching. That,
Basic feasible is not feasible.
no, any basic feasible is feasible, but some feasible solutions are not basic feasible.
Why is it beneficial to narrow down our search?
Would you rather search infinitely many things or finitely many things? It's much better to have a finite space to search through. And so the whole point of narrowing down to basic feasible is we are really winnowing the possibilities. And the idea is to have some kind of algorithm that will allow us to move among the basic feasibles very quickly. And so again, right now it's not clear how this is going to help us, other than the fact that we're now restricting ourselves to it is sufficient to study a finite set rather than studying a set that's potentially infinite. So at this point, it's not clear why the algorithm is going to work better on feasible solutions than, on basic feasible solutions than feasible solutions. At this point, it's a leap of faith that it seems like it should be a good thing to restrict the number of solutions we need to look at, the number of things we need to check. I can't prove to you that it's good at this point, but it seems like we're making progress. Okay? So it's not a proof, but it does seem like we're making progress. So now what we want to do is we want to prove if a feasible solution exists, a basic feasible solution exists. So I think this is called, I think this gets bumped up to a theorem, yes. So theorem, if a feasible solution exists, a basic feasible exists. Right? So what this is essentially telling us is, look, imagine you have a solution that's not basic feasible. What does it mean if it's not basic feasible? Yes? So the columns are not linearly independent. So what I can do is I'm going to somehow play a game and remove one of the columns from consideration and replace it with linear combinations of the other columns in play. And I'm going to keep doing this until I have a set of columns that's linearly independent. Now, while I'm doing this, I have to make sure that my vector x stays non-negative. That's going to be a little bit hard. I've got to be very careful about that. Okay, question? Yes? What I'm going to do is I'm going to assume that there is a feasible solution with a minimal number of non-zero entries. And I'm going to get a contradiction. So the idea is assume x is feasible with fewest non-zero entries. If x is basic feasible, is it hard to prove a basic feasible solution exists? No, okay? If x is basic feasible, you've got a basic feasible solution. Okay? And without loss of generality, may assume x is not basic feasible. We're going to get a contradiction. And the way we're going to get a contradiction is we're going to form a new feasible solution that has fewer non-zero entries. That's going to contradict the minimality assumed here. Okay? You may have seen this proof technique in linear algebra. Depending on who you have as an instructor, depending on which theorems you prove, this idea of having a set with a certain kind of minimal property, this is used very often in linear algebra. So let's assume xj1 aj1 plus xjk ajk equals b, but the aj's are not linearly independent. What does it mean for the aj's to be non-linearly independent? It means some combination of them equals 0. Therefore, we can find gamma j1 aj1 plus gamma jk ajk equals 0. We can assume not all the gamma ji's equals 0. Without loss of generality, let's assume gamma j1 is greater than 0. There's a limit to how much I want to write on the board when I only have one board to play with. Why can I do this? Well, look, I have a linear combination. Because they're linearly dependent, I can do this where the gamma's not all 0. So if the gammas are not all 0, one of them has to be either positive or negative. If it's negative, I can multiply by -1, and then it's still going to equal 0, and I can make it positive. I can relabel my indices so that for convenience, it's the first entry that's non-zero. Does it really matter which entry is 0 or non-zero? Does it matter which index? Do we have enough indices floating around in this problem? Right? We've already got x sub j sub I. Let's call it a day, okay? This is a very common technique in linear algebra. Without loss of generality, if needed, relabel, reindex, so the first coordinate is where things happen. Okay? So if this is true, Can I multiply the equation through by lambda and still have this true? I can even take lambda to be 0 and it's still true. And now we subtract. And now, after we subtract, we get xj1 minus lambda gamma j1, aj1 plus xjk minus lambda gamma jk, ajk equals b. What we've just shown is we have a new vector. I'll call it x sub lambda. And we have a prime times x sub lambda equals b. And I'll just write that over here. A prime x lambda equals b. Is x lambda a basic solution? I'm sorry, is x lambda a feasible solution? Does it solve ax equals b? Yeah, because since this equals 0, no problem. What's the only danger that might make this not a feasible solution? Why might it not be a feasible solution? Yes?
One of the x's might become negative.
Oh, that would be bad, right? Can anybody give me a value of lambda where this will be a feasible solution? 0. Who's the smartass who said 0? Thank you. Why does that work?
Because then all the xji's are just xji.
Yeah, then xji is xji. You start and end at the same place. So when lambda equals 0, it's feasible. These numbers here are all positive. I can increase lambda. Think of lambda as a dial. I can turn it up a little bit. And as long as I don't turn it up too much, I can't subtract so much that this becomes positive, that this becomes negative. So feasible at lambda equals 0, lambda small. Now I keep dialing up lambda. Lambda is getting larger and larger and larger. What's got to happen eventually? I'm sorry? One of the terms is going to become 0, or maybe two of the terms. Some number of terms are simultaneously going to become 0. It may not be the first one. But eventually, as I turn things up, these are all getting larger if gamma j is positive. If gamma j is negative, it doesn't matter. As I turn lambda up, eventually one of these terms has to become 0. Worst case scenario, the first one is going to become 0 once I take lambda to be xj1 over gamma j1. So we know at most xj1 divided by gamma j1. So once I go up that high, I know I'm going to have the first component become 0. Probably I'll get to 0 before then. But the nice thing is, as I increase lambda, for every value of lambda, the coefficients are positive, 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 positive. By continuity, intermediate value theorem, I can't go from positive to negative without going through 0. So at some critical value of lambda, I now get one of these entries has become 0. And when it becomes 0, I now have a feasible solution with fewer columns. So at critical lambda, get feasible with fewer non-zero columns. And that's a contradiction. So increase lambda, eventually get feasible with fewer non-zero columns. And that's the contradiction. Yes?
This might be very obviously impossible, but what if all the x's become 0 together?
If they all become 0 together, I think then this is a good proof of why we need to consider the special case when
They're all 0 together. They couldn't be 0. Wouldn't p have to be a
Okay, good. Excellent.
That would be
Excellent. That's much better than the bullshit I was about to do. Yes. I like that. If they're all 0, then what's going to be true about B? Also 0. So the only way we could have this is if we are trying to say AX equals the 0 vector.
Or your bottom thing would be a multiple of B on the right-hand side instead of the 0 vector.
I like the first one. I like B being 0. Because when it comes up, if all the stuff over here becomes 0, then B has to be the 0 vector. And so this is where you often have these non-degeneracy assumptions, is we're going to assume that B is not the 0 vector.
So are you saying lambda small is at most x j1 over?
Yep.
Why
Be-
the first one?
Well, because we know all the x's are non-negative. In fact, all the x's are positive. We assumed without loss of generality one of the gammas is positive. Let's say it's gamma 1. So once lambda is as large as xj1 over gamma j1, this factor here is now xj1. This difference is now going to be 0.
So we're just arbitrarily saying that it's the first one that.
We're arbitrarily saying the first index is the one that's positive. We know one of the indices has to be positive in this linear combination because it's dependent. Why not make it the first one? And so by doing that, that allows me to make the argument very clean. Otherwise, I would have to say maybe it's J sub L, and it's the Lth one that's going to have the action happening. Just to make things a little bit easier, let's just relabel and assume it's the first one. And it's extremely important that we know we can't send lambda to infinity. When we get to the simplex method later, we actually will have that as a possibility. Is we could have a solution whose cost is going all the way to minus infinity. Here, that can't happen. So what we've shown here is that if we have a linear dependency and we have a feasible solution, we can somehow replace one of the non-zero x's and have its effect taken over by a bunch of other ones. And then this is just lather, rinse, repeat. You can keep doing this until you're left with something that's linearly independent. Or we assume that this was the fewest number. We got one that it was even fewer. Contradiction. What was the only thing we assumed? We assumed x was not basic feasible. So from this, we immediately conclude if you're a feasible solution with the fewest number of non-zero entries, then you must be basic feasible. The corresponding columns must be linearly independent. All right, so this is a good place to stop. We did a lot of linear algebra here today. We'll do a little bit more linear algebra on Monday when we talk about optimal solutions. There sadly wasn't time today to talk about the Euclidean algorithm problem. I do want to cover that next week because this is a really good problem in terms of thinking about how to approach things. Okay.